In a Greenland ice core drilled from roughly 2 meters below the surface, scientists found a boundary they did not expect. Not a gradual fade, not a slow transition, but a single layer thin enough to hold between 2 fingers where the oxygen isotopes shift by 15 degrees Fahrenheit within what appears to be a single decade. Above that layer, a world still warming from the last great ice age. Below it, the world before the Younger Dryas reset. The question that layer quietly poses has not been fully answered in 30 years of looking. That boundary dates to somewhere around 12,800 years ago, give or take a generation. At that moment, the planet had been warming for centuries. Ice sheets that had pressed down across Canada and northern Europe were pulling back. Animals were spreading into new ranges. Small groups of people were beginning to do something they had rarely done before: stop moving. Build. Stay. Then the cold came back. Tonight we'll follow 3 traces of what may have happened and what it left behind. We'll move through the evidence held in the ice, through the layers of ancient lake sediment, and through the pattern of human sites that were occupied one season and quietly abandoned the next. We won't arrive at a single conclusion. The record is too fragmented, and the science too unsettled for that kind of certainty. But the traces are there, and some of them are strange enough that they deserve a slow and careful look. The world the Younger Dryas interrupted was not yet civilized in any way we would recognize. There were no cities, no writing, no organized agriculture, but there were people, perhaps a few million of them, scattered across every continent except Antarctica, and some of those people were for the first time beginning to experiment with permanence. In the region we now call the Levant, communities were harvesting wild grains in quantities large enough to store. In parts of what is now Turkey and Syria, groups were returning to the same locations year after year, shaping the land slightly around their presence. Something was building. Slowly, experimentally, but building. The cold interrupted it. What the cold actually felt like on the ground is something we can only approach sideways, through the thinning of pollen layers in lake cories, through the retreat of forest species recorded in upland sediment, through the shrinking of campsites and the disappearing of certain kinds of stone tools from the archaeological record. None of these are direct testimonies. They are at best traces of responses, people moving, people changing what they hunted, people adjusting their shelter, their clothing, their roots trying to stay inside the margins of a world that within a single human lifetime may have shifted from something livable into something that demanded every adaptation they had. Here is where one detail becomes difficult to set aside. In certain sites distributed across North America, parts of Europe and the Middle East, sites that sit precisely at the sediment layer marking the start of the Younger Dryas, researchers have found concentrations of platinum and iridium at levels hundreds of times above the geological background. These are elements uncommon in Earth's surface rocks. They are, however, common in objects that originate beyond the atmosphere. Whether those elevated concentrations represent a signature of something that arrived from space, or whether they carry a more terrestrial explanation, is a question that some researchers have spent careers arguing over without resolution. But the concentrations are real, and they are positions sitting in the same thin layer as the black carbon as the temperature collapses. The final appearance of Clovis campsites across North America is the kind of alignment that the record keeps refusing to let go of. There are several competing explanations for what the ice cores recorded 12,000 years ago, and tonight we will give each of them room. The meltwater theory, which traces the catastrophe to the collapse of enormous ice-dammed lakes and the sudden flooding of the North Atlantic with fresh water, carries considerable weight. It fits known film and physics. It matches marine sediment records. It echoes in the foraminifera, the tiny shelled creatures whose cold water species replace warm water ones in the North Atlantic record at precisely this moment. The cosmic impact hypothesis is more contested, but the layer of evidence it rests on has proven harder to dismiss than many initially expected. And beneath both of these possibilities sit the slower forces, volcanic cycles, shifts in atmospheric methane, the subtle wobble of Earth's orbit that may have already been nudging the climate toward a threshold before anything acute arrived. None of these explanations standing alone fully accounts for what the ice shows. The cooling was too sudden, too global, too symmetrical. And when it ended, when temperatures rose again by something close to 10 degrees in what may have been less than a decade, what emerged on the other side was a world that almost immediately began to move in directions it had never moved before. Agriculture appeared, permanent settlement expanded. At Göbekli Tepe in what is now southern Turkey, people were hauling stones that weighed several tons and carving them with precision right at the moment the long cold was finally lifting. Whether that surge of construction and cultivation was coincidence, or whether something about enduring 1200 years of disruption created the conditions for it, remains one of the quieter questions this record raises. It is not a question with a clean answer, but it is the kind of question that changes how you look at every trace we will encounter tonight: the abandoned campsites, the platinum-laced sediment, the magnetic spherules scattered across 2 continents, the mammoth populations that carried healthy genetics right up until they didn't. We begin as the science itself begins with the ice, the layer that should not exist. In 1993, at a research station on the Greenland ice sheet, a drilling team pulled a core sample from roughly 2 meters below the current surface and laid it under fluorescent light. The core was white, mostly compressed snow from centuries of accumulation, each annual layer readable the way tree rings are readable, a slow and reliable calendar extending backward through time. The team had been measuring oxygen isotope ratios preserved within each layer, using the chemistry of ancient snowfall as a kind of thermometer. Under normal conditions, those ratios shift, gradually tracking the gentle rise and fall of global temperature across decades and centuries. The record is patient, incremental, and almost meditative in its regularity. This one was not regular. At a specific depth, a layer no thicker than a man's hand is wide, the isotope ratios dropped by a value equivalent to roughly 15 degrees Fahrenheit. Not across a century of slow cooling, not across several decades of gradual transition, but within what the resolution of the core could detect as a single decade. Some analyses of comparable cores have suggested the compression may be even tighter than that, as few as 3 annual layers separating the warm world from the cold one. The scientists reading this record in the early 90s had the instruments to confirm what they were seeing. What they did not have, and what the field continues to work through today, is a complete and agreed-upon explanation for how the planet's temperature could move that far that fast without leaving a cause as clear as the effect. That boundary has a name. We call it the onset of the Younger Dryas, and it marks one of the most discussed and least fully resolved transitions in the entire Quaternary climate record. The name itself comes from a flower Dryas octopetala, a small Arctic plant with 8 white petals adapted to tundra soils capable of surviving in conditions that barely sustain biology. In the geological layers of sites across northern and central Europe, this plant appears suddenly in the sediment record, not accumulating gradually as part of a slow ecosystem shift, but arriving the way cold arrives, displacing the pollen of oak and elm and hazel that have been advancing northward for 2,000 years of relative warmth. One layer shows forest. A few annual deposits later it shows tundra. The little white flower does not explain itself. It simply records that something changed, and that it changed in what amounts in geological terms to an instant. And that is where the quiet problem begins, because ice core records are not unique to Greenland. Cores drilled from the Antarctic ice sheet carry a record of the same period. So do cores extracted from glaciers in the Alps and the Andes, from ice fields in Iceland and the high peaks of Central Asia. When researchers compare these records across hemispheres, they find a coherent signal not identical in magnitude, not perfectly simultaneous in every archive, but pointing consistently in the same direction. The world did not cool gradually at the end of the last ice age's retreat. It warmed, stabilized, then warmed again during a period we call the Alarod interstadial, and then by some mechanism or combination of mechanisms still under active debate, that warming stopped and reversed within a time frame that has no comfortable parallel in the preceding millennia. The event we are following tonight spans roughly 1,200 years, from approximately 12,800 to 11,700 years before the present. During this interval, average temperatures across much of the northern hemisphere appear to have been 10 to 15 degrees Fahrenheit, lower than they were during the preceding warm phase. To hold that number for a moment, this was not a minor fluctuation, not a cold decade or a difficult century. This was a sustained planetary scale reversal, arriving at the precise moment when the last great ice age had seemed to be losing its grip on the world. Pollen records from lake sediments in Switzerland show oak forest replaced by tundra grass within a single depositional layer. Marine sediment cores from the North Atlantic show a sudden replacement of warm water foraminifera species with cold water ones at the same stratigraphic horizon. Cave formations in China speleothems whose oxygen isotope chemistry tracks monsoon rainfall record a collapse in Asian precipitation of 30 to 40% that persisted for the duration of the cold interval. The signal is not regional, it is global, and it is abrupt. What the ice and sediment record does not tell us on its own is what caused it. Several mechanisms have been proposed, each supported by evidence, each carrying its own unresolved complications. The most widely accepted explanation involves a disruption of ocean circulation in the North Atlantic, specifically the system of currents that moves warm tropical water northward along the surface and returns cold, dense water southward along the ocean floor. This system is sensitive to the balance of salt and freshwater in the surface ocean, and at the time of the Younger Dryas onset, that balance was under pressure from an unusual source, the catastrophic drainage of enormous ice-dammed lakes across North America, releasing volumes of fresh water into the Atlantic that may have been large enough to stall or significantly weaken the circulation. A second explanation, more contested and considerably more dramatic, points to anomalous materials found in sediment layers at dozens of sites across 2 continents, concentrations of platinum, iridium, nanoscale diamonds and melted mineral spherules at levels that some researchers argue cannot be produced by any terrestrial process at the concentrations observed. Both threads will occupy us in the chapters ahead. But before we reach the mechanisms, it is worth pausing on the world that existed just before this boundary, the world that the cold interrupted. The Allahud warm interval was not simply a climatic episode, it was a moment of expansion. Megafauna populations were recovering range. Forests were advancing into territory that had been tundra for 10,000 years, and scattered across multiple continents, small groups of people were beginning cautiously and experimentally to stay in one place. Not cities, not organised agriculture, but something quieter. The first sustained attempts at permanence at building shelter meant to last more than a season at returning to the same ground year after year. The Younger Dryas interrupted most of those attempts. What grew from the ruins of them 12 centuries later is where the second half of this story lives. We follow the first thread now, the ocean, the ice dams, and the mechanism that most climate scientists still consider the most probable cause of what the isotope record recorded in that thin, cold layer in the Greenland core. The conveyor that stopped. One of the oldest oceanographic metaphors compares the Atlantic's circulation system to a conveyor belt, warm water, riding northward along the surface, releasing its heat into the atmosphere above Europe and the North Atlantic, then cooling, growing denser, sinking to depth and returning southward along the ocean floor in a slow, cold underflow that has been running more or less continuously for millions of years. The metaphor is imperfect, as all metaphors are when applied to systems of this complexity, but it captures something essential. This is a system that moves heat, and it moves a great deal of it. Estimates suggest the Atlantic meridional overturning circulation. The technical name for this pattern transports more thermal energy northward than all of the world's rivers combined carry in volume. Without it, the average winter temperature in London would more closely resemble that of northern Labrador. The current is not a luxury of the climate system. It is for the populations living near the North Atlantic basin, one of its most consequential features. It is also, as researchers have known for several decades, a system with a vulnerability. The sinking that drives the circulation, the downwelling that pulls warm surface water northward to replace it, depends on density, and density in seawater depends on 2 things, temperature and salinity. Cold, salty water sinks. Warm or fresh water does not. The system is self-sustaining under stable conditions, but it is not infinitely robust. Introduce enough fresh water into the surface of the North Atlantic, and the density gradient that drives the downwelling weakens. If the freshwater input is large enough and sustained enough, the sinking can slow substantially, or in certain model scenarios stall almost entirely. When that happens, the northward transport of heat slows with it. The regions that depend on that transported warmth grow cold, and they grow cold not over centuries but over the span of years, to decades, as quickly as the ocean surface can reorganize itself under new conditions. This is the mechanism that most climate scientists still consider the most probable primary driver of the Younger Dryas, and the source of the freshwater disruption in the leading version of this theory was not rain, and not a gradual increase in glacial melt. It was a catastrophic release, sudden, enormous, and almost certainly without precedent in the human experience of the time. The detail is specific and it refuses to go away. At the height of the last ice age meltwater draining off the Laurentide ice sheet, the vast continental glacier that covered most of Canada and the northern United States had been accumulating behind natural ice dams along the retreating margin of the ice. The largest of these impounded bodies of water is known today as Lake Agassiz, named for the 19th century naturalist who first recognized evidence of its existence in the landscape of the Canadian interior. At its maximum extent, Lake Agassiz covered an area larger than all of the modern Great Lakes combined. It held by some estimates more fresh water than any lake that has existed on Earth since the last ice age ended. It was held in place by ice, and ice, given enough time and enough warming, eventually fails. The geological record of Lake Agassiz's drainage history is written in the landscape itself, in the wave-cut terraces visible on hillsides across Manitoba and Saskatchewan, in the ancient shorelines that now sit hundreds of feet above any modern water body in the channels it is scoured into bedrock by flows of water moving at volumes that dwarf anything the modern hydrological system produces. What the record shows is that the lake did not drain gradually. It drained in pulses, sometimes catastrophically, when ice dams gave way under the accumulated pressure of water and warmth. The question that bears most directly on the Younger Dryas is not whether these drainage events happened. The evidence for them is well established, but whether one of them happened at the right time in the right direction and at sufficient volume to disrupt North Atlantic circulation enough to trigger 1,200 years of cold. Marine sediment cores from the floor of the North Atlantic carry a partial answer. At the stratigraphic horizon corresponding to the onset of the Younger Dryas, those cores show a sudden and pronounced increase in the freshwater signal preserved in the chemistry of foraminifera. The microscopic shelled organisms whose calcium carbonate tests record the temperature and salinity of the water they lived in. The cold water species replace the warm water species abruptly. The isotope chemistry shifts in ways consistent with a large influx of fresh water diluting the surface ocean. Something changed the composition of the North Atlantic surface at this moment, and it changed it quickly. Whether the volume and routing of Lake Agassiz's drainage can fully account for the magnitude of the disruption is where the debate becomes technical and at times unresolved. Some reconstructions suggest the lake drained eastward through the St. Lawrence system, delivering its volume directly into the Atlantic. Others propose a northern routing through the Mackenzie River Valley toward the Arctic Ocean, which would still have affected circulation, but through a different pathway and with different timing. The drainage routes have left physical traces in the landscape, but those traces are difficult to date precisely enough to settle the argument with confidence. What the meltwater theory does well is explain the Northern Hemisphere signal, the rapid cooling of Europe, the retreat of forest in the British Isles, the advance of sea ice across the North Atlantic, and the suppression of the westerly wind patterns that normally carry maritime warmth into the continent's interior. What it explains less cleanly is the global dimension of the Younger Dryas signature, particularly the records from the Southern Hemisphere that show contemporaneous changes in climate that a North Atlantic circulation disruption would not obviously reach. Some researchers account for this through atmospheric teleconnections and what is known as the bipolar seesaw, the tendency of the two hemispheres to exchange heat in opposite directions when Atlantic circulation weakens. Others remain less certain, and their uncertainty opens a door to the possibility that the meltwater mechanism, however well supported, may not have acted alone. That possibility is where the next layer of the record begins, a layer that is in some respects even harder to explain away than freshwater in the North Atlantic. The layer that fell from above. A thin band of sediment appears at dozens of archaeological and geological sites across North America, parts of Europe, and as far east as the Levant. It is darker than the layers above and below it, and it sits at the precise stratigraphic horizon, marking the onset of the Younger Dryas. Archaeologists working Clovis sites in the American Southwest and Great Plains began encountering it decades ago, noting that the distinctive fluted spear points of the Clovis culture appeared consistently below this layer and almost never above it. They called it the black mat, a descriptive name for a descriptive feature, and for many years it was understood primarily as a marker of ecological change, a layer of organic rich sediment deposited after the abrupt shift to colder, wetter conditions that followed the Alarud warmth. The black mat was a boundary, and boundaries in stratigraphy are useful. They help you organize time. For a while that organizational usefulness seemed sufficient. Then researchers began looking more carefully at what the black mat actually contained. The carbon in the layer was not simply organic debris from dying vegetation. It was in significant part the kind of carbon produced by combustion, fine-grained black carbon consistent with the residue of large-scale burning. Not a single fire. Not a regional episode of drought-driven ignition, but something more distributed. Charcoal and soot appearing at the same stratigraphic level across sites, separated by thousands of miles in sediment archives that had no other obvious connection to each other. The burning signal showed up in lake cores from the American Midwest in ocean sediments off the coast of California, in peat deposits in parts of Western Europe. It appeared, in other words, to be a record of fires that burned across multiple continents at approximately the same time. What could ignite forests and grasslands simultaneously across that geographic range is a question the layer does not answer by itself, but it narrows the list of plausible causes considerably. And then the chemistry became stranger still. Beginning in the early 2000s and accelerating through the following decade, a series of studies reported concentrations of platinum and iridium in the black mat layer at levels several hundred times above the background. Concentration in surrounding sediments. These are not elements that accumulate in surface geology under ordinary circumstances. Both platinum and iridium are sidrophile metals. They have a strong chemical affinity for iron, and in the early history of the solar system they sank with iron into the cores of rocky bodies including the Earth. What remains in the Earth's crust is a small and relatively uniform residue. But in objects that formed in space and were never differentiated into a core, asteroids, comets and their fragments, these elements occur at much higher concentrations. Finding them elevated by orders of magnitude in a single sediment layer at a specific moment in time at geographically distributed sites is the kind of pattern that demands some account of where the material came from. Some researchers have proposed natural terrestrial explanations: cosmic dust accretion, localized geological anomalies, or contamination in the sampling process. And those explanations have been tested and retested across multiple independent studies with variable results. The spike is real in many of the records. Whether it is real everywhere it has been reported, and whether the variations between sites represent sampling issues or genuine geographic heterogeneity in the depositional event, remains an active point of contention. The platinum and iridium are not alone. Within the same horizon, researchers have reported the presence of nanoscale diamonds, tiny crystalline carbon structures that form under conditions of extreme pressure and rapid heating of the kind produced by high-velocity impacts or by the shockwaves that propagate through rock and sediment when a large extraterrestrial object enters the atmosphere at cosmic velocity. Nanodiamonds are found naturally in some meteorites, and they have been produced in laboratory simulations of impact conditions. Finding them distributed across the black mat layer in samples from sites in North America and parts of Europe is consistent with the signature one might expect from a body entering the atmosphere and delivering a high-energy pulse to the surface or near-surface environment. The presence of magnetic spherules, tiny rounded particles of melted and rapidly cooled rock with iron-rich compositions and textures characteristic of extreme thermal processing adds another element to the same assemblage. Spherules of this kind are produced by asteroid and comet impacts, by nuclear detonations and by certain industrial process. In sediment layers 12,000 years old, the industrial explanation is unavailable. The question is whether natural extraterrestrial infall, the continuous slow rain of micrometeorite material that falls on the Earth's surface at a background rate, could account for a concentrated layer, or whether the concentrations observed require a discrete high-energy event. One site has provided what some researchers consider the most difficult piece of this assemblage to explain through ordinary processes. At Abu Huraira in northern Syria, a site occupied by one of the earliest sedentary communities in the archaeological record excavations recovered glass-like material embedded in the sediment at the Younger Dryas boundary. Analysis of this material found that it had formed at temperatures exceeding 2,200 degrees Celsius. To hold that number in context, the melting point of iron is approximately 1,500 degrees Celsius. The temperatures required to produce the glass recovered at Abu Huraira are not reached in ordinary wildfires, not in volcanic activity at the surface, and not in any geological process the site's stratigraphy otherwise records. The two mechanisms known to produce silicate glass at those temperatures in a surface context are high-velocity cosmic impact and nuclear detonation. The melt glass at Abu Huraira sits in the same layer as elevated platinum concentrations alongside charred plant material and the disrupted archaeological deposits of a community that appears to have been permanently displaced by whatever event the layer records. The site does not prove a cosmic impact, but it presents a combination of features that the meltwater theory alone does not easily account for, and that the geological record of the period has not yet produced a clean alternative explanation for. What the impact hypothesis proposes in its current form is not a single large crater forming a collision of the kind that ended the Cretaceous. It proposes instead a fragmented body, a comet or asteroid that broke apart during atmospheric entry and delivered its energy across a broad swathe of the northern hemisphere, in a series of airbursts and possible surface contacts primarily over or near the Laurentide ice sheet. The absence of a confirmed crater, which is the most frequent objection raised against this hypothesis, may be accounted for by the ice itself, a target that absorbs and redistributes impact energy without preserving the kind of permanent scar that rocky ground retains. Whether that accounting is sufficient is the question that takes us directly into the debate this theory has generated and into the evidence on both sides of it. That debate begins in the next chapter, and it is quieter than it sounds. The people who were there. What does it mean for an entire way of life to disappear from the record? Not a population reduced, not a culture diminished, but a distinct and geographically widespread pattern of human behavior recognizable by its tools, its hunting strategies, its particular approach to working stone that appears across an entire continent. And then within the stratigraphic resolution available to archaeology stops appearing. The Clovis culture is one of the most studied and most debated chapters in North American prehistory, and one of the things that makes it so difficult to interpret is precisely this quality of apparent completeness. The Clovis people did not leave behind a record of gradual decline. They left behind a record, and then they left behind silence. The tools themselves are worth describing because they are unusual in ways that matter. Clovis points are large bifacially worked projectile points, shaped from flint chert or obsidian with a precision that required considerable skill and practice. Their most distinctive feature is a longitudinal flute, a channel removed from the base of each face that allowed the point to be hafted securely to a wooden or bone foreshaft, creating a weapon capable of penetrating the thick hides of the megafauna that constituted the primary prey of the people who made them. These points are found from the Pacific coast to the Atlantic seaboard, from southern Canada to the northern reaches of Mexico, always associated with the same general toolkit, always at the same general stratigraphic level. Whatever the Clovis culture was, a single population, a shared technology, a broad tradition carried by related groups, it spread across a continent with a speed and coherence that suggests both mobility and adaptability of a high order. And then the distinctive points disappear from the record at precisely the horizon where the black mat layer sits. Above the black mat, the Clovis point does not appear. This is not an absence created by poor preservation or sampling bias. The sites are numerous, and the layers above the black mat contain archaeological material from later periods. Something changed the material culture of the people living in North America at this boundary, and it changed it completely. The detail is small in the sense that a single tool type is small, but it refuses to go away because the Clovis disappearance does not stand alone. It is accompanied in the same stratigraphic intervals by the extinction of the animals. Those tools were designed to hunt. Mammoths, mastodons, ground sloths, saber-toothed cats, dire wolves, short-faced bears, American horses, American camels, 35 genera of large mammals in North America alone gone from the fossil record within a few centuries of the Younger Dryas onset. The coincidence of timing between the human cultural disruption and the faunal collapse is one of the most discussed and least resolved problems in quaternary science. The overkill hypothesis. The argument that human hunters arriving in the Americas drove megafauna to extinction through unsustainable predation has been part of this debate for decades, and it carries genuine evidential support. The correlation between human arrival and megafaunal collapse appears on multiple continents and at multiple time periods. Australia lost its giant marsupials around 45,000 years ago, broadly coinciding with the earliest evidence of human presence. Madagascar lost its elephant birds and giant lemurs within centuries of Polynesian settlement. New Zealand lost its way within a few hundred years of the arrival of the Maori. The pattern is consistent enough to take seriously, but the North American case does not fit it as cleanly as those island and isolated continent examples do, because the timing of the extinctions in North America clusters not at the point of human arrival, but at the point of the Younger Dryas boundary thousands of years after people and megafauna had been sharing the continent. Some researchers argue that the Clovis people represented a new and more efficient hunting culture that pushed already stressed populations over a threshold. Others find the lag between arrival and extinction too long to sustain the hunting pressure explanation without invoking additional stressors. Those additional stressors were at the Younger Dryas onset considerable. Mammoth DNA recovered from fossil specimens and analysed in the past 2 decades has produced one of the more unsettling findings in this area of research. The genetic evidence for mammoth population shows no sign of inbreeding, no contraction of diversity, no signal of the slow demographic decline that precedes most well-documented extinctions. The populations appear by genetic measure to have been healthy until very close to their disappearance. That pattern is more consistent with a rapid externally imposed collapse than with the slow attrition of hunting pressure alone, and it sits in an uncomfortable alignment with the black mat layer, the platinum spike, and the melt glass at Abu Yera. Whether the alignment is causal or coincidental is the question that neither the overkill hypothesis nor the climate disruption theory fully resolves on its own. There is a further dimension to the Clovis disappearance that is easy to overlook in the focus on tools and megafauna. The sites that show Clovis occupation, the camps, the kill sites, the lithic scatters that record where people stopped and worked stone, are not just absent above the black mat. Some of them show signs of abrupt abandonment. Tools left mid-process refuse patterns that suggest departure, rather than orderly relocation hearths that were not cleaned or maintained in the way that a community expecting to return would leave them. The archaeology of abandonment is an interpretatively difficult field, and these observations carry uncertainty, but they are consistent with a picture of disruption that was neither gradual nor anticipated, a world that changed faster than the people living in it could organise a response to. What happened to those people and to the communities forming on the other side of the Atlantic at the same moment is where the record takes us next. The extremens that were interrupted. A wild einkorn wheat grain is roughly 5 millimeters long. It is not much to look at a small hard seed enclosed in a tough husk, designed by millions of years of selection pressure to survive drought, cold, and the grinding of animal teeth. In the sediment layers of early Natufian sites in the Levant, these grains appear in concentrations that tell a particular story, not the scattered presence of a plant incidentally present in the landscape, but the accumulated residue of deliberate collection, processing, and storage on a scale that implies something more organised than opportunistic foraging. The people who left these grain deposits were not farmers in any sense we would recognise today, but they were doing something that sits at the edge of that category, returning to the same locations season after season, harvesting wild stands of grain with flint-bladed sickles whose use-wear patterns are preserved in the archaeological record, and grinding the harvest on stone platforms that were too heavy and too carefully positioned to be the tools of a fully mobile people. They were in a meaningful sense learning what a plant could become under sustained human attention. And then the Younger Dryas arrived and the wild grains failed. The Natufian culture of the southern Levant centered on the region that today encompasses parts of Israel, Jordan, Lebanon, and Syria represents one of the most intensively studied examples of the transition towards sedentism in the archaeological record, beginning around 14,500 years ago. During the warming that preceded the Younger Dryas, Natufian communities were building semi-permanent structures, maintaining cemeteries, and developing what appears to be a rich, symbolic and material culture expressed in carved bone ornaments, decorated tools, and burial goods that suggest differentiated social roles and a community life sustained across seasons, rather than scattered by migration. Sites like Ain Malaha in the Jordan Valley and Wadi Hameh in what is now Jordan show architectural remains substantial enough to have required collective labour and a commitment to place that is qualitatively different from the archaeological signature of fully mobile hunter-gatherer groups. The Natufian world in the centuries before the Younger Dryas onset was moving towards something. The direction of that movement, interrupted by 1,200 years of cold and failing harvests, is one of the more poignant questions the period raises. What the cold did to the Levant is legible in the sediment sequences and the site records. The wild cereal grasses that had supported dense Natufian harvesting in the Jordan Valley and on the slopes of the Fertile Crescent retreated upslope and northward as temperatures fell and the effective moisture available to the landscape decreased. Lake levels in the Dead Sea Basin dropped. The oak and pistachio woodlands that had provided reliable plant foods contracted. Several Natufian sites show evidence of abandonment in the centuries following the Younger Dryas onset, and those that continue to be occupied show a shift in the material record. Less evidence of heavy-duty grinding equipment. More evidence of hunting returns. A repertoire of food procurement that looks less like the focused harvest of a people settling into a landscape and more like the diversified strategy of a people negotiating with a landscape that was no longer offering what it had. The pattern recurrence across the Levantine record is striking not a single community's story of disruption, but a regional signature of interrupted development that appears consistently across dozens of sites and several cultural subphases of the Natufian sequence. The site of Abu Huraira, on a terrace above the Euphrates in what is now northern Syria, provides one of the most detailed records of this transition. Before the Younger Dryas, the occupants of Abu Huraira were harvesting at least 150 plant species from the surrounding landscape, including large quantities of wild rye and einkorn wheat gathered in sufficient volume to require substantial storage. The faunal record from the same layers shows a broad spectrum of animals: gazelle, wild cattle, onager, a range of smaller mammals and birds exploited with the confidence of people who know their landscape intimately and have time to be selective. Then in the layers corresponding to the cold interval, the plant diversity collapses. The wild cereals disappear from the record. The faunal assemblage shifts toward a narrower range of species, and the cut marks on the bones become more thorough, the kind of processing that extracts every caloric return from a carcass, rather than the selective butchery of people with reliable access to the next meal. It is in the layers, just at or shortly after the Younger Dryas boundary, that some researchers identify the first unambiguous evidence of deliberate planting at Abu Huraira grains, with the morphological changes associated with domestication beginning to appear alongside the last records of the wild harvested forms. Agriculture at this site may not have been an invention born of abundance. It may have been a solution developed under the pressure of scarcity by people who remembered what the land had once offered, and were trying through deliberate intervention to make it offer that again. Across the Mediterranean and northward into Europe, a broadly analogous story unfolds at a different cultural register. The Hamburg culture of northern Europe reindeer hunters who had expanded into the tundra margins left by the retreating Scandinavian ice sheet during the Allerød warmth contracted southward as the cold returned, following the animals they depended on back into refugia that had sustained hunter-gatherer populations during earlier cold periods. Forest cover in parts of Britain and northern France dropped by estimates approaching 80% within the Younger Dryas interval, and the archaeological record in those regions becomes sparse in ways that suggest genuine population reduction rather than simple migration. The communities that had been consolidating along river valleys and coastal terraces during the warming dispersed again. The first tentative moves toward the kind of aggregated settlement that the Natufian was experimenting with further south simply did not happen in northern Europe during the cold interval. They would happen, but later and under different conditions. What all of these regional stories share is a structure expansion interrupted experiments, paused adaptations forced by a climate that withdrew its support without warning. The record of how people responded to that withdrawal across a dozen different landscapes and a dozen different cultural contexts is the record of how humanity learned under duress to negotiate with the natural world on terms the natural world had not previously required. And in some of those negotiations, something new and durable was being made. What the skeptics heard science does not progress through consensus alone, and the history of the Younger Dryas debate is in part a history of productive disagreement. The impact hypothesis in particular has attracted sustained and serious criticism from researchers who have looked at the same sediment layers, run their own analyses, and arrived at different conclusions, not through dismissiveness, but through the application of the same evidentiary standards the hypothesis's proponents claim to meet. Those criticisms deserve careful attention because they are not peripheral objections from the margins of the field. They come from geochemists, archaeologists, and climate scientists whose work on this period spans decades, and whose discomfort with the cosmic impact interpretation is grounded in specific technical and often difficult to dismiss concerns. The platinum and iridium concentrations reported at the Younger Dryas boundary are perhaps the most cited piece of evidence for an extraterrestrial event, and they are also the piece of evidence that has proven most difficult to replicate consistently. Several independent research teams working with sediment samples from sites in North America and Europe where the original platinum spike was reported have found either no anomaly or anomalies far smaller than those in the initial studies. The variability between studies is itself informative. If the platinum spike were the uniform signature of a single large event depositing extraterrestrial material across a broad geographic area simultaneously, one would expect it to appear with some consistency across well-sampled sites within that area. The patchiness of the replication record does not disprove the original findings, but it raises a legitimate question about whether the elevated concentrations represent a discrete depositional event or whether they reflect localized geological processes, differential preservation, or in some cases contamination introduced during sampling or laboratory preparation. Platinum is not rare in all geological contexts. It occurs in elevated concentrations in certain volcanic rocks and in association with some types of soil formation, and disentangling a genuine extraterrestrial signal from geological background noise at concentrations that are already near the limits of reliable detection is a genuinely difficult analytical problem. The nanodiamonds present a related difficulty. The original reports of nanodiamond concentrations in the Younger Dryas boundary layer were striking, and the mechanism proposed to explain them, rapid carbon compression under impact shockwave conditions, is physically coherent. But subsequent studies have questioned both the identification and the interpretation. Some researchers argue that the particles identified as nanodiamonds in the boundary layer samples are misidentified graphene or graphite structures that can form under a variety of conditions, including ordinary wildfires at high temperatures. Others have pointed out that nanodiamonds fall on the Earth's surface as part of the continuous micrometeorite flux at a background rate sufficient under certain depositional conditions to produce apparent concentrations without requiring a discrete impact event. The debate over the nanodiamonds has generated more published rebuttals and counter-rebuttals than almost any other single line of evidence in this field, and the current state of the literature is, to be direct about it, genuinely unresolved. Some researchers consider the nanodiamond evidence compelling. Others consider it an artifact of identification methodology. Both groups are working with real data, and the disagreement is not about values or interpretation. In the broad sense, it is about chemistry and microscopy, which makes it harder, not easier, to resolve through argument alone. The absence of a crater remains the most intuitively powerful objection to the impact hypothesis, and it is worth taking seriously on its own terms rather than simply deferring to the ice target explanation that proponents offer. Airbursts, the atmospheric explosion of an incoming body before surface contact, are real phenomena, and the 1908 Tunguska event demonstrated that a body large enough to flatten 2,000 kilometers of Siberian forest could do so without leaving a conventional impact structure. But the Tunguska event, for all its violence, did not trigger a global climate shift lasting 1,200 years. Scaling the hypothesized Younger Dryas impactor but to a size capable of producing the observed effects requires postulating an object or a cluster of fragments whose atmospheric energy release would have been orders of magnitude larger than Tunguska. And the absence of any confirmed surface expression of an event at that scale is a genuine evidentiary gap. The Hiawatha impact structure beneath the Greenland ice sheet has been proposed as a candidate, but its age remains uncertain, and current dating efforts have not produced results that confidently place its formation at the Younger Dryas boundary rather than at some earlier or later period. A hypothesis that depends on a crater we cannot find in ice that has since melted is asking the evidentiary record to carry a weight it may not be able to support. And yet the pattern returns. This is the discomfort that the skeptical position must also account for, and it is not a small discomfort. This meltwater theory, the leading alternative, explains the North Atlantic circulation disruption, the European cooling, the marine sediment record, and the freshwater signal in the foraminifera chemistry with considerable coherence. It does not explain the black carbon layer distributed across multiple continents. It does not explain the melt glass at Abu Huraira formed at temperatures no wildfire reaches. It does not explain why the platinum concentrations, however inconsistently replicated, appear at all at the Younger Dryas boundary in a range of independent studies using different methodologies at different sites. The meltwater theory is physically well-founded and empirically supported, but it is a theory of ocean circulation, and the black mat layer is not an ocean circulation phenomenon. The two explanations are not in principle mutually exclusive. A cosmic airburst over the Laurentide ice sheet could have delivered both the surface signatures and the meltwater pulse that stalled the circulation, but invoking both requires accepting the cosmic component that the skeptical position is reluctant to accept without a confirmed impact structure. It may be natural, it may be chance. The discomfort is that the pattern does not fully dissolve under scrutiny from either direction, and the field has not yet produced a single framework that accommodates all of the observations without remainder. What the skeptics have done, and done well, is prevent premature closure on a question that the evidence does not yet support closing. What the evidence has done, despite their best efforts to explain it otherwise, is continue to sit in the record layer by layer, waiting for a more complete account. The people who lived through the event did not have the luxury of waiting. Their record is written not in sediment chemistry, but in the choices they made, the places they left, and the things they built when the cold finally lifted. The long winter's arithmetic, consider a bone needle. It's approximately 8 centimeters long, carved from the fibula of a small mammal, polished smooth by use with an eye at one end, no wider than 2 millimeters a hole, drilled through dense cortical bone by a tool we have not recovered with a precision that implies both experience and intention. Needles of this type appear in the archaeological record of multiple cold climate sites during the Younger Dryas interval, and they represent something specific, not simply the presence of people who worked bone, but the presence of people who were sewing fitted garments. A needle with an eye produces a different kind of stitch than an awl, and a different kind of stitch produces a different kind of clothing tailored, close-fitting, capable of sealing against wind and wet in ways that a simple wrapped hide cannot. The appearance of this tool type in greater frequency during the cold interval is a quiet piece of evidence easy to overlook in discussions of climate catastrophe and megafaunal collapse, but it carries its own information about us, about the texture of survival during the Younger Dryas, methodical, incremental, and driven by the most immediate of imperatives. The arithmetic of cold is not complicated, but it is relentless. A human body at rest generates roughly 80 watts of thermal energy, enough to maintain core temperature in still air at around 10 degrees Celsius, without additional insulation. Below that threshold, the margin between comfort and hypothermia narrows with each degree of temperature reduction, and the Younger Dryas at its depth may have pushed average temperatures in the mid-latitudes of the northern hemisphere down by 10 to 15 degrees Fahrenheit from the preceding warm interval. The practical consequence of that shift for people living in open landscapes without permanent shelter was that the energy budget of daily life changed fundamentally. More calories were required to maintain body heat, more time had to be spent acquiring fuel for fire, more effort went into the construction and maintenance of shelter, and the construction of shelter capable of surviving a Younger Dryas winter was not a simple task. Archaeological sites from this period show adaptations in hearth-designed fire pits dug deep aligned with heat-retaining stones positioned within structures whose floor plans were made smaller and lower to reduce the volume of air that needed to be warmed. In some sites in Eastern Europe and the Russian plain where wood had become scarce, as the tree line retreated, mammoth bones were used as structural supports and fuel, simultaneously, a dual use that speaks to the efficiency forced by scarcity. The shift in diet visible in the faunal assemblages of Younger Dryas sites is one of the more legible aspects of the survival record. Before the cold, the bone deposits at Clovis and Natufian sites tell a story of focused high-return hunting. Mammoth mastodon large bovids, the megafauna that provided caloric returns large enough to sustain a group through days of preparation and transport. After the onset of the cold, and accelerating as the megafauna declined, the assemblages diversify sharply downward in body size. More rabbit, more hare, more bird, more fish. The arithmetic of this shift is significant and worth holding. For a moment, a single mammoth could provide several tons of usable meat, fat, and marrow, enough to sustain a group of 25 people for several weeks. To replace that caloric return with rabbits requires somewhere in the range of several hundred animals, each requiring its own hunt, its own processing, its own investment of energy in pursuit and capture. The net caloric return per hour of foraging effort falls dramatically when the primary prey shifts from megafauna to small game, and that fall has direct consequences for group size mobility patterns and the amount of time available for any activity other than food acquisition. Microliths, the small geometrically precise stone blades that appear in greater variety and abundance across European and Asian sites during and after the Younger Dryas, are the tool form that corresponds to this dietary shift. They are not simply smaller versions of earlier tools. They are differently designed, optimized for hafting into composite weapons, arrows, spears with multiple cutting edges, traps with triggered mechanisms that change the efficiency of small game hunting in ways that a large bifacial point cannot. The appearance of microlithic technology at roughly this period across geographically separated regions is one of the cleaner examples of convergent technological innovation in the Paleolithic record, different peoples working in different landscapes with different raw materials arriving at a similar solution to the shared problem. Whether that convergence reflects cultural diffusion along population contact networks, or independent invention driven by the same ecological pressures, is a question the distribution of the tools alone cannot settle. But the pattern and recurrence of microlithic assemblages appearing where the megafauna disappeared across a time frame that aligns with the Younger Dryas suggests the technology and the crisis were connected. Social organization almost certainly shifted alongside the material culture, though the archaeology of social structure is always the most inferential aspect of this kind of reconstruction. In periods of resource abundance, small family bands can sustain themselves independently, dispersing across a landscape to exploit its resources without the coordination cost that larger groups impose. In periods of scarcity, the calculus changes. A sick hunter, an injured elder, a nursing mother unable to contribute to the food quest, these are manageable contingencies within a larger, mutually supporting group in ways they are not within a band of 6 or 8. Several Younger Dryas sites show evidence of larger aggregations than the preceding period. More individuals sharing a single shelter, more hearths in proximity refuse patterns suggesting a communal organization of food processing rather than household-level preparation. Whether these aggregations reflect permanent coalescence of previously separate bands or seasonal gatherings driven by the concentration of surviving game herds, the shift toward larger and more interdependent groups during the cold interval is consistent with what population ecology would predict under sustained resource stress. What the arithmetic of survival ultimately required, and what the record of the Younger Dryas hints at imperfectly but repeatedly, was not only the invention of new tools and the aggregation of larger groups, but the development of a new relationship between human communities and information that men had held collectively. The knowledge of where game moved, which plants survived the cold at which elevations, where springs remained unfrozen through winter, which roots connected one viable territory to another. This knowledge distributed across a group and transmitted deliberately through teaching and story was as much a survival technology as the bone needle or the microlith, and it left its own kind of trace in the record, quieter than a stone tool but perhaps more durable. That trace becomes more visible as the cold begins finally to lift. The world that froze together. The distance between the Greenland ice sheet and the Huascarán Glacier in the Peruvian Andes is roughly 11,000 kilometers. The two ice bodies have no physical connection to each other, no shared drainage basin, no common atmospheric circulation pattern in the ordinary sense, no mechanism by which a change at one location would be expected to register at the other within any timescale shorter than decades of climate reorganization. And yet when researchers extracted an ice core from the Huascarán summit in the early 1990s and measured the same oxygen isotope ratios that had revealed the abrupt cooling in the Greenland record, they found the same signal. Not identical in magnitude, not perfectly synchronized at the resolution available from tropical ice archives, but present a cooling registered in the chemistry of Andean snowfall at the same general period as the temperature collapse, recorded at the top of the world. The Younger Dryas was not a North Atlantic event that the rest of the planet witnessed from a distance. It was something the entire climate system participated in, and the question of how a disruption centered in the North Atlantic could reorganize climate patterns across both hemispheres simultaneously is one of the more technically demanding problems the record poses. The mechanism proposed to account for the Southern Hemisphere signal is called the bipolar seesaw, and it describes a feature of the global climate system that has been observed in the paleoclimate record across multiple cold periods, not only the Younger Dryas. When Atlantic meridional overturning circulation weakens or stalls, the northward transport of heat from the tropics is reduced. That heat does not disappear from the system. It accumulates in the South Atlantic and Southern Ocean, producing a modest warming in Antarctic records at precisely the moments when Greenland is cooling most sharply. The Antarctic ice cores confirm this pattern for the Younger Dryas interval, while Greenland temperatures were dropping by 15 degrees Fahrenheit. The Antarctic record shows a slight warming trend, a thermal surplus produced by the redistribution of heat that the stalled Atlantic conveyor was no longer moving northward. The seesaw is real, and in its operation helps explain how a North Atlantic circulation event could have global consequences. But the seesaw is a redistribution mechanism, not an amplification one, and the changes recorded in tropical and southern hemisphere archives during the Younger Dryas are in some cases larger than a simple heat redistribution would predict. The Asian monsoon record is one of the more striking examples of this excess. The speleothems of Dongye Cave in southern China cave formations, whose oxygen isotope chemistry tracks the strength and origin of monsoon precipitation with a temporal resolution. Finer than most other paleoclimate archives, show a collapse in monsoon intensity at the Younger Dryas onset that persisted for the duration of the cold interval. The reduction in effective precipitation reconstructed from these records approaches 30 to 40% relative to the preceding warm phase, a change large enough to have restructured the hydrology of river systems across South and East Asia, and to have substantially reduced the productivity of the landscapes that supported human populations in those regions. A weakening of the Atlantic conveyor affects the monsoon through its influence on the position of the intertropical convergence zone, the band of intense convective rainfall that migrates seasonally between hemispheres, and whose position is sensitive to the temperature gradient between the North and South Atlantic. When the North Atlantic cools, the convergence zone shifts southward, reducing moisture delivery to the Asian landmass. The physics of this teleconnection are understood well enough to reproduce in climate models, which gives the monsoon collapse a mechanistic account, even if the full magnitude of the observed change pushes against what the models comfortably produce. Lake Titicaca, sitting at nearly 4,000 meters above sea level, on the Altiplano between Peru and Bolivia, holds its own archive of the Younger Dryas in the chemistry and sediment texture of its ancient lake bed deposits. Core records from the lake show a significant reduction in water level during the cold interval, a drawdown produced by the same shift in atmospheric circulation that suppressed the Asian monsoon operating through a different pathway across South America. The pollen preserved in the same cores shows a vegetation shift consistent with cooling and drying the retreat of the warm adapted plant communities that had expanded during the Alaro warmth, replaced by the hardier sparse cover assemblages characteristic of high-altitude cold conditions. Glaciers in the surrounding Andes, which had been retreating during the preceding warm phase, advanced again. Their moraines, the ridges of rock and sediment bulldozed forward by the moving ice, are preserved in the landscape at positions that correspond by cosmogenic dating to the Younger Dryas interval. The ice remembered the cold long after the cold had ended in the physical displacement of stone. In Africa, the picture is complicated by the continent's latitudinal range and the multiple circulation systems that govern its different climate zones, but the signal is present. The Eastern African rift lakes Tanganyika, Malawi, Victoria show reduced levels and increased salinity during the Younger Dryas, consistent with a southward displacement of the rain-bearing circulation that normally delivers moisture to the equatorial belt. Lake Victoria, whose basin had filled only recently during the preceding warm and wet period, experienced a dramatic reduction in inflow. In the Sahara, the brief greening that would fully develop during the African humid period, the so-called Green Sahara of the early Holocene, was delayed. The grasslands and lakes that would eventually make the Sahara a viable human landscape for several thousand years did not establish themselves until after the Younger Dryas cold had finally released its grip on the atmospheric patterns that govern North African precipitation. What all of these records share, read together, is a coherence that the meltwater theory can partially account for, and that the climate models partially reproduce, but that neither mechanism nor model fully closes. The world cooled together, and it did so in ways that reached into every inhabited landscape, simultaneously restructuring the conditions of survival for every human community on the planet. That restructuring left traces everywhere, and some of those traces scattered across the globe point in a direction that the meltwater theory alone has difficulty explaining. The fires in particular are difficult to account for without something that moved faster than an ocean current. When the cold released its hold around 11,700 years ago, the Greenland ice cores record a warming that mirrors the cooling at the onset of the Younger Dryas in one critical respect: its speed. The temperature signal does not ease upward across centuries of gradual amelioration. It rises by the same oxygen isotope measure used to track the initial collapse by approximately 10 degrees Fahrenheit within a decade, possibly within a shorter interval than that compressed into what some annual layer analyses suggest may have been as few as 3 to 5 years of rapid transition. The cold that had taken perhaps a single human lifetime to establish was undone in roughly the same span of time. If you had been born at the end of the Younger Dryas, you may have lived to see the tundra bloom, the tree line advance, the rivers run year-round again, and the first sustained warmth of what would become the Holocene, all within your own memory, within the compass of a single life's experience of the world. That speed is worth dwelling on because it shapes everything that follows. A gradual warming over centuries would have allowed ecosystems, animal populations, and human communities to adjust incrementally, tracking the shifting climate the way migrating species track a retreating frost line steadily, with some predictability, with time to test new strategies before the old ones became fully obsolete. The warming that ended the Younger Dryas did not offer that kind of time. It delivered the new conditions almost as abruptly as the cold had arrived, and the human communities that had spent 1,200 years developing survival strategies calibrated to a cold and depleted world found themselves within a generation or two in a landscape that was transforming faster than it could be mapped by experience. The animals that had survived the cold by contracting their ranges and diversifying their diets were suddenly presented with expanding resources. The people who had learned under duress to extract maximum return from minimum input were suddenly operating in a world where the margins were widening. What they did with those widening margins is one of the more remarkable chapters in the human record, and one of the more difficult to account for by purely incremental explanations. The earliest confirmed monumental construction in the archaeological record, Göbekli Tepe on a limestone ridge in what is now southeastern Turkey, was built within approximately 2 centuries of the Younger Dryas termination. The site consists of multiple circular enclosures defined by anti-shaped limestone pillars, the largest of which stand more than 5 meters tall and weigh in excess of 10 tons. The pillars are decorated with carved relief images of animals, foxes, snakes, vultures, scorpions, wild boar, rendered with a naturalistic confidence that implies a well-developed artistic tradition rather than a first experimental attempt. The enclosures were not residential structures. They contained no hearths, no storage pits, no sleeping surfaces, none of the features that characterize habitation sites in this period. Whatever they were built for, and the debate over their function remains genuinely open. They were built for a purpose that required the organized labor of hundreds of people over an extended period, coordinating the quarrying, transport, and erection of stone masses that no small family band could have moved. The detail that sits uncomfortably alongside every attempt to explain Göbekli Tepe as a product of its time is this: the people who built it were, by the material evidence of the surrounding landscape and the faunal record of the site itself, still hunter-gatherers. There is no confirmed evidence of domesticated plants or animals in the earliest layers at Göbekli Tepe. The inhabitants of the surrounding region were feeding themselves from wild herds and wild harvests, as their ancestors had done throughout the Younger Dryas, and yet they were organizing labor at a scale that most archaeological frameworks associate with the surpluses and social hierarchies of early agricultural communities. The conventional sequence, agriculture first, then surplus, then monument building, does not fit Göbekli Tepe without considerable adjustment. Some researchers have proposed inverting the sequence that the organizational demands of building and maintaining a site like Göbekli Tepe may have been what drove the intensification of food production in the surrounding region, creating the pressure toward deliberate cultivation rather than following from it. Whether this inversion is correct or whether the site represents something more complex and less linear than either the sequence captures is a question the excavations at the site ongoing since the 1990s have continued to complicate rather than resolve. What Göbekli Tepe does represent with reasonable certainty is a community's investment of enormous collective energy in something that was not in any immediate sense necessary for survival. It was built when the cold had just ended, when the world was demonstrably warming, when the wild resources that had contracted during the Younger Dryas were recovering and expanding. The urgency of the cold interval, the bone needles, the deepened fire pits, the diversified hunting strategies the aggregated social groups had passed or was passing. And in the space opened by that receding urgency, something else was emerging. Some researchers describe Göbekli Tepe as a ritual centre, a gathering place for communities spread across a wide territory who came together at intervals to maintain a shared symbolic and ceremonial life. Others read it as a monument to collective memory, a physical inscription of something that the communities who built it needed to mark, needed to make permanent in stone in a way that fires and stories and portable objects could not. What they needed to mark in this misting is the crisis they had come through. The long cold, the failing harvests, the contraction of the world, and the survival that followed it. The 1200 years of the Younger Dryas were by demographic estimates reconstructed from the genetic record and the archaeological density of sites, a period of significant population reduction across much of the inhabited world. The communities that emerged from the cold interval were in some regions descended from bottlenecked populations that had passed through a severe contraction groups whose genetic diversity had narrowed under the pressure of sustained resource stress, and whose cultural traditions had been condensed, lost, or radically transformed by the same pressure. The warming did not simply restore what the cold had taken. It opened a new landscape populated by people who had been changed by what they had survived, equipped with tools and organizational capacities and perhaps a quality of collective memory that the pre-Younger Dryas world had not required them to develop. That transformation from the compressed adaptive survival culture of the cold interval to the expansive monument-building crop experimenting communities of the early Holocene did not happen everywhere at the same pace or in the same form, but it happened across a remarkable range of independent cultural contexts at a remarkable proximity in time in ways that suggest the pressure of the Younger Dryas and the release of its ending had shaped something fundamental in how human communities understood their relationship to the land, to each other, and to the possibility of permanence. The next question is what that transformation looked like from the ground up in the soil, in the seeds, and in the first careful choices of which plants to tend and which animals to keep. The first deliberate ground. A domesticated einkorn wheat grain is distinguishable from its wild ancestor by a single structural feature, the rachis. In wild wheat, the rachises. The small segment of stem that connects each grain to the plant's central spike is brittle by design, fracturing at maturity to scatter the seeds across the ground through the natural movement of wind and passing animals. This brittleness is the plant's reproductive strategy refined across millions of years of selection. A harvester collecting wild wheat accelerates that scattering with every stroke of a sickle, losing a significant portion of the harvest before it reaches the processing floor. In domesticated wheat, the rachis is tough. The grain clings to the spike until deliberately removed by the threshing. This single change from shattering to non-shattering is the botanical signature of domestication, and it does not happen by intention. It happens because the harvesters who repeatedly return to the same stands of grain, cutting before full maturity to reduce shattering losses, are inadvertently selecting for the rare individuals whose rachis holds a little longer. Over generations of this inadvertent selection, the proportion of tough rachis plants in the harvested population increases, and the wheat becomes, without anyone deciding to make it so, something new. The process is slow, measured in centuries rather than decades, and its beginning is invisible in the archaeological record because the first stages leave no morphological trace that distinguishes them from ordinary wild harvesting. What the record eventually shows at sites like Abu Huraira, at Ain Ghazal in the Jordan Valley, at Chayenu, in southeastern Turkey, is the end point of that invisible process with grain assemblages in which the proportion of tough, righteous individuals has risen above what random natural variation would produce, signalling that human harvesting pressure has begun to reshape the plant's genetics. The dating of these transitions, refined by advances in ancient DNA analysis over the past 2 decades, places the earliest unambiguous domestication signatures in the Fertile Crescent within a few centuries of the Younger Dryas termination. The timing is not coincidental in any obvious sense, and it is not fully explained by the warming. Alone, the climate had been warm before during the Alarud interstadial, without producing the same outcome. What the Younger Dryas appears to have contributed is not simply a warm period for plants to grow in, but a human population that had spent 1,200 years learning under conditions of scarcity exactly how much the landscape's productivity mattered and exactly how little of it could be taken for granted. The domestication of animals followed a related but distinct trajectory shaped by different biological and social constraints. The earliest confirmed domestic sheep and goats appear in the archaeological record of the Zagros Mountains and the Taurus foothills within roughly a millennium of the Younger Dryas termination, their bones distinguishable from wild counterparts by changes in the size and shape of the limb, elements produced by captive management and selective breeding. Cattle and pigs followed at different sites and with different timing across the broad arc of the Fertile Crescent and its margins. What all of these domestication events share is a precondition, a human community settled or semi-settled, enough to maintain sustained contact with an animal population across multiple generations close enough and consistent enough in its presence to begin reshaping the animal's behaviour and eventually its genetics. That kind of sustained proximity requires a degree of territorial commitment that the fully mobile hunter-gatherer lifestyle does not easily accommodate. The Younger Dryas, by forcing communities into smaller and more carefully chosen territories, and by developing the social structures necessary to maintain larger aggregated groups through long cold seasons, may have created precisely the conditions under which sustained human-animal proximity became possible and eventually productive. The dogs were earlier than all of this, and their history is tangled enough to deserve its own careful treatment. Genetic studies of modern and ancient dog populations suggest that the divergence of domestic dogs from their wolf ancestors occurred somewhere between 15,000 and 40,000 years ago, with a wide confidence interval that reflects genuine uncertainty in the molecular clock estimates and in the interpretation of the fossil record. What is less contested is that the burial practices surrounding dogs change markedly in the period following the Younger Dryas graves, in which a human and a dog are interred together, with a deliberateness of placement that implies emotional, rather than purely utilitarian significance appear at sites across the Levant, Central Asia, and Europe from around 12,000 years ago onward. A burial from the site of Ein Malaha in northern Israel, dated to approximately 12,000 years before the present, contains the remains of an elderly person, with one hand resting on the skeleton of a puppy. The gesture is preserved in bone across 12 millennia, as a legible record of attachment. Whatever the dog's practical value as a hunting partner, a guard animal or a source of warmth in the cold shelters, this burial suggests that the relationship had developed dimensions that went beyond utility, and that those dimensions were worth marking at death. The spread of agriculture from its earliest centres in the Fertile Crescent was neither rapid nor straightforward, and the model of a single origin from which farming diffused outward across the Old World has been substantially revised by ancient DNA evidence, showing that domesticated crops and animals spread through a combination of cultural transmission and population movement, with local hunter-gatherer communities in different regions independently developing their own relationships with local plant and animal species. Rice domestication in the Yangtze Valley. Millet cultivation on the Yellow River, yam and sorghum management in sub-Saharan Africa, squash and eventually maize in Mesoamerica. These were not dependent inventions derived from a single Fertile Crescent source. They were convergent solutions developed by communities in different landscapes, who had been shaped by different versions of the same Younger Dryas pressure, and who emerged from the cold interval with the same fundamental reorientation toward the productive management of the living world around them. That reorientation did not produce agriculture everywhere at once, and it did not produce it painlessly. The transition from a diverse wild food diet to one dominated by a small number of cultivated species carried health costs that the skeletal record documents clearly increased. Dental caries from starchy foods, this reduced skeletal robusticity from less physically demanding foraging, elevated rates of nutritional deficiency diseases in populations dependent on grain monocultures, The early farmers were not healthier than the hunter-gatherers who preceded them, at least not individually. What they had was something different from individual health. They had the capacity to produce and store surplus to support population densities that mobile foraging could not sustain, and to maintain the kind of settled communities in which the next transformation of the human record became possible. That transformation was not only agricultural, it was architectural, symbolic and social, and its earliest physical expression had already been rising from the limestone plateau of southeastern Turkey for several generations. The architecture of memory, at Jericho in the Jordan Valley, the earliest defensive stone wall yet identified in the archaeological record, stands approximately 3.7 meters high and is associated with a tower whose internal staircase carved from solid stone was still structurally sound when excavators reached it in the 1950s. The tower is roughly 8.5 meters in diameter at its base, with walls more than a meter thick, and it predates the invention of writing by several thousand years. Its construction required the coordinated labour of a community large enough to quarry, transport and position hundreds of tons of stone over an extended period, and it was built not in response to a known military threat. The evidence for organised warfare in the region at this period is ambiguous at best, but for reasons that the structure alone cannot fully explain. Whether the tower served primarily as a defensive structure, as a storage facility, as a ceremonial monument, or as some combination of purposes, the modern category system does not cleanly accommodate it, but it stands as one of the earliest surviving expressions of a human impulse that the Younger Dryas had done nothing to diminish, and perhaps everything to intensify the impulse to build something that would outlast the people who built it. The community at Jericho that constructed this tower was living within a few centuries of the Younger Dryas termination in a landscape whose productivity had been transformed by the return of reliable rainfall and the recovery of the wild grain stands that Natufian communities had been harvesting before the cold interrupted them. The site had been occupied intermittently since the Natufian period, one of those locations whose combination of permanent spring water, fertile alluvial soil and access to multiple ecological zones made it a recurrently attractive settlement regardless of the wider climatic context. But the scale of investment represented by the tower and wall at Jericho's pre-pottery Neolithic phase is qualitatively different from anything that preceded it at the site, and the difference is not only architectural. The community building this structure was also burying its dead beneath the floors of its houses, and in some cases removing the skulls of the deceased after an interval of decomposition, plastering them with lime into realistic facial portraits and integrating them into the life of the household as objects that were handled, displayed, and eventually carefully interred. The plastered skulls of Jericho and the related practice found at Ain Ghazal and other early Neolithic sites in the Levant are among the most discussed artefacts of this period, and their interpretation remains genuinely open. But what they suggest at minimum is a community in which the boundary between the living and the dead was maintained as a permeable and actively managed relationship in which ancestors were kept present in a literal physical sense, rather than honoured at a distance through symbolic gesture alone. The significance of this practice read against the background of the Younger Dryas is difficult to separate from the demographic reality of what communities had survived. A population that had passed through a severe bottleneck that had watched across 50 generations of cold, the contraction of its world, the loss of animals and plants, and perhaps entire communities whose names were preserved in stories long after the people themselves were gone, carried a particular relationship to the dead that a population living in stable abundance might not have developed. The ancestors of Jericho's early Neolithic community were not remote figures from a mythologized past. They were in a meaningful genealogical sense the survivors, the specific individuals whose choices, adaptations and endurance during the Younger Dryas had produced the living community now building in stone. Keeping their faces present in plaster beneath the floors of houses that were themselves an expression of a newly recovered permanence may have been a way of maintaining that connection, of insisting on the continuity between the people who had survived the cold and the people who were at last building something that could last beyond a single winter. The symbolic life of the early post-Younger Dryas communities was not confined to burial practice. The carved pillars of Göbekli Tepe, the painted and incised stones of Djerf el Amer in northern Syria, the carved anthropomorphic figurines found across a broad arc of the Fertile Crescent in Anatolia, these objects represent an investment of skilled labour in the production of meaning that goes well beyond what survival strictly requires, and their concentration in the centuries immediately following the Younger Dryas termination is one of the more striking patterns in the material record of the period. Some researchers have proposed that the symbolic efflorescence of the early Neolithic represents a kind of release, the flowering of expressive capacities that the cold had suppressed, not by eliminating them, but by redirecting the energy they would have consumed toward the more immediate demands of staying warm and finding food. Others have suggested that the ritual and symbolic elaboration of this period was functionally connected to the social demands of larger, more complex communities, that the shared ceremonies and shared symbols expressed in these objects were the technologies by which groups of hundreds of people drawn from previously separate bands maintained the cohesion necessary to coordinate labour at the scale that monument building and early agriculture required. And that is where this quiet problem returns, because both of these explanations may be true simultaneously, and neither fully accounts for the speed and geographic breadth of the symbolic expansion that the early Holocene record shows. The genetic legacy of the Younger Dryas bottleneck is visible in the population structure of modern humans, though the signal is subtle, and its interpretation requires care. Studies of mitochondrial DNA diversity and Y chromosome haplogroup distributions in populations across the Old World show patterns consistent with severe demographic contraction followed by rapid expansion, the genetic signature of a population that passed through a narrow point and then spread outward from a small number of surviving founders. The timing and location of these bottlenecks reconstructed from molecular clock estimates overlap with the Younger Dryas in ways that are suggestive without being definitive. What the genetics cannot tell us, and what the archaeology can only approach obliquely, is what was lost in the contraction: the languages, the ritual systems, the accumulated ecological knowledge, the names of places and the stories attached to them, all the non-material content of human cultural life that leaves no direct trace in sediment or bone. The survivors of the Younger Dryas rebuilt from what they carried in memory and in practice, and the civilization that emerged from that rebuilding was in a real sense shaped as much by what had been lost as by what had been preserved. What the record of the post-Younger Dryas world suggests, taken as a whole, is not a story of simple recovery, of a world paused and then resumed. It is a story of transformation in which the pressure of 1,200 years of cold produced communities that were in ways both measurable and immeasurable, different from the communities that had existed before the cold arrived. They built differently, buried their dead differently, related to the plants and animals they depended on differently, and organized themselves at scales and with a degree of internal complexity that the pre-Younger Dryas world had not yet required them to develop. The cold did not create civilization, but it may have created, through the long pressure of survival and the abrupt release of its ending, the human communities capable of beginning it. What remains after all the sediment chemistry and the faunal records and the architectural remains is the question of what this story means for the world those communities eventually produced, and for the one we are living in now. The Holocene and its edges, the warm period we are living in, has a name. Geologists call it the Holocene, and it began by the most widely accepted chronology approximately 11,700 years ago, at precisely the moment the Younger Dryas released its hold on the planet's temperature and the oxygen isotope record in the Greenland ice cores began its rapid ascent back toward warmth. The Holocene is, by the standards of the Quaternary climate record, an unusually stable interval. The oscillations between cold and warm that characterized the preceding glacial period, the rapid climate shifts known as Dansgaard-Eschger events, the Heinrich stadials, the Younger and Older Dryas intervals, have no counterpart in the Holocene records of comparable magnitude. For roughly 11,700 years, the planet's climate has remained within a relatively narrow band of variability, and it is within that band, and arguably because of it, that everything we call civilization has developed. Agriculture cities, writing trade networks, legal systems, the accumulation of knowledge across generations. None of these things are impossible in principle during periods of greater climate instability, but none of them had developed to any significant degree before the Holocene began. The coincidence of timing between the onset of sustained climatic stability and the emergence of complex human societies is not, most researchers would argue, a coincidence at all. What the Younger Dryas sits at the edge of, then, is not simply a cold interval in the middle of a warming trend. It sits at the boundary between two fundamentally different modes of human existence: the mobile, adaptive, small-scale societies of the Pleistocene on one side, and the settled accumulative monument-building societies of the Holocene on the other. The cold interval was not the cause of that transition in any simple mechanical sense, but it occupies the boundary in a way that makes it impossible to tell the story of the transition without accounting for what the cold did to the people who lived through it, and for what the ending of the cold released in the communities that survived. The Younger Dryas is the hinge on which the door between those two worlds turns, and the door, once it swung open in the early Holocene, did not close again. This is worth holding carefully because it cuts against a narrative of progress that places civilization at the end of an ascending line of human development, the inevitable product of growing intelligence, expanding population, and accumulated technological sophistication. The record does not support that cleaner story. The people of the Alaroa interstadial in the warm centuries before the Younger Dryas were cognitively indistinguishable from the people who built Göbekli Tepe and plastered the skulls at Jericho. They were equally intelligent, equally capable of symbolic thought, equally equipped with the biological hardware that would eventually produce agriculture and cities. What they lacked was not capacity. What they lacked was the specific combination of ecological pressure, demographic reorganization, and accumulated adaptive knowledge that 1,200 years of cold produced in the communities that came through it. The Younger Dryas did not make humans smarter. It made certain humans in certain places desperate and organized in ways that the relatively abundant world of the Alaroa had not required them to become. The genetic bottleneck that the Younger Dryas appears to have contributed to left a mark that is still readable in the population structure of modern humans, however faintly. We are in a real, if partial sense, descended from the survivors, from the specific subset of the pre-Younger Dryas human population, whose circumstances, choices, and perhaps luck allowed them to pass through the cold interval and emerge on the other side with enough demographic momentum to rebuild and expand. The people who did not survive the communities whose sites show abandonment without reoccupation, whose genetic lineages ended in the cold, are present in the record only as absences, as the sites that stop producing material culture above a certain layer as the haplogroups that should appear in modern populations and do not. What they knew, what they believed, what languages they spoke, and what names they gave to the rivers and mountains of their territories, all of this is gone. Not gradually eroded by time, but abruptly cut off at the boundary the little white flower marks in the sediment. The question the Younger Dryas asks of the present is not one that the geological record can answer, and it would be a misreading of what the evidence shows to treat the past as a simple template for the future. The mechanisms that drove the cold interval, the possible disruption of Atlantic circulation, the possible contribution of an extraterrestrial event, the cascade of ecological feedbacks that sustained the cold for 12 centuries are not straightforwardly analogous to the dynamics shaping the current climate. The world has changed too much. The human footprint on the climate system is too different in kind from the natural forcings of the Pleistocene, and the uncertainties in both the paleo-climate record and the current climate projections are too large to support confident translation from one context to the other. What the record does support more modestly and perhaps more usefully is a certain quality of attention, an awareness that the stability of the Holocene is a feature of a specific interval, not a permanent property of the planet, and that the climate system's capacity for abrupt reorganization is documented in the record with a clarity that is difficult to read and then set aside. The ice cores are still down there in the darkness below the Greenland surface, holding their record in the chemistry of ancient snow. The black mat layer still sits at its stratigraphic horizon in dozens of sites across 2 continents, still carrying its carbon and its platinum, and its unanswered questions about what fell or what failed at that precise moment 12,800 years ago. The plastered skulls of Jericho, the carved pillars of Göbekli Tepe, the bone needle with its 2mm eye, all of these things are still present in the record, still legible, still refusing to resolve themselves into a single clean narrative about what happened, and why, and what it means. The Younger Dryas does not offer conclusions. It offers a record partial and fragmentary and strange, in places of a world that changed faster than the people living in it could anticipate, and of what those people made of the world that remained. We have been reading that record tonight, slowly layer by layer, the way the ice itself was laid down, one cold season at a time, accumulating towards something we are still learning to understand, The drilling team that pulled the GISP-2 core from the Greenland ice in 1993 was looking for data. They found it in the oxygen isotope ratios in the compressed annual layers in the thin hand width of sediment that held a 15-degree temperature shift within what may have been a single decade. They laid the core under fluorescent light and read what it contained. What they could not read, and what no instrument available to them could measure, was the weight of what that layer represented, the full human texture of the world that existed below it, and the world that existed above it. And the 1,200 years of cold and loss and improvisation and endurance that separated the two. The core held the chemistry. The rest is inference and patience and the slow accumulation of evidence from lake beds and cave formations and the bones of people who never knew they would be studied. That is in some ways the condition of all historical knowledge. We are always working from fragments from the things that happen to survive, in the things that happen to be preserved, read by instruments and interpretive frameworks that were not present at the event and cannot fully recover it. The Younger Dryas is not unusual in this respect. It is simply more honest about it than most chapters of the past, because the gaps in the record are large enough to see clearly, and the competing explanations are coherent enough that none of them can be dismissed without remainder. The platinum is in the sediment or it is not consistently there. The melt glass formed at 2,200 degrees, or it did not. The Lake Agassiz drainage disrupted Atlantic circulation, or it arrived too late or through the wrong channel to have done so alone. These are not questions of interpretation in the soft sense. They are questions of measurement and chemistry and dating precision, and the field has not yet produced answers with enough resolution to close them. There is something restful in the end about that incompleteness. Not the restfulness of giving up, but the restfulness of recognizing that the record is what it is. A partial archive of an event that was too large, too fast, and too long ago to leave behind a complete account of itself. The people who lived through the Younger Dryas did not need to understand it to survive it. They needed fire and shelter and the bone needle, and the knowledge of where the rivers ran unfrozen through the worst of the cold. They needed each other. They carried what they could carry, and they left behind what the ground has kept for us, which is not everything, but is more than nothing, and is in certain lights extraordinarily strange and beautiful. Somewhere in that record, in the grain assemblages of Abu Huraira, in the carved limestone of Göbekli Tepe in the hand, resting on the puppy's skeleton at Ain Malaha, there is a quality of recognition that crosses the distance of 12,000 years without diminishing. These were people who had lost a great deal, and were carefully and collectively beginning to build again. What they built outlasted the cold that had interrupted them, some of it in the form of the crops they domesticated and the organizational habits they developed, is still present in the world we move through every day, so thoroughly absorbed into the fabric of ordinary life that its origins in crisis and scarcity and the slow work of survival are almost invisible. Almost. One thing the record does not resolve is whether the memory of the cold persisted in the stories those communities told, whether the myths of lost golden ages and world-ending winters that appear in cultures across the Northern Hemisphere carry, somewhere in their oldest layers, a genuine echo of the Younger Dryas. It is the kind of question that cannot be answered with sediment chemistry. It can only be held lightly as a possibility that somewhere in the oldest narratives we have inherited, the little white flower is still blooming at the edge of a landscape that was, not so very long ago, tundra. Rest now. Dreamer. The ice is still down there, holding its record in the dark. The layer is still exactly where it was thin, precise, and patient in a way that only stone and cold and time can be patient. Whatever it contains, whatever fell or failed or flooded at that particular moment 12,000 years ago, it will still be there when morning comes. The questions it raises are not the kind that require an answer tonight. They are the kind that keep the way the ice itself keeps slowly in layers, adding depth with each passing year. Let the cold of that ancient winter be distant now, and the warmth that followed it close. Let the weight of 12 centuries of endurance settle into the ground, somewhere far below where it belongs. The survivors found their way through. The record remembers them in its fragmentary and imperfect way, and you tonight need carry none of it further than this. Sleep well. The long winter ended. It always does.